So this is Introduction to Composite Materials, online lecture series 3, Micromechanical Analysis of Composite Material. The topic, Micromechanical Analysis. So my name is Samayat Fanta, PhD scholar at Indian Institute of Technology, Kanpur, Department of Aerospace Engineering. So for any query, you can use my email address. Objective of lecture 3 is developing the concept of volume and weight fraction of fiber and matrix, density and void fraction in composite. Find the 9 mechanical and 4 hydrothermal constants, 4 elastic moduli, 5 strength parameters, 2 coefficient of thermal expansion and 2 coefficient of moisture expansion of unidirectional lamina from the individual properties of the fiber and the matrix, from fiber volume fraction and the fiber packing or the fiber packing density. Discuss the experimental characterization of the 9 mechanical and 4 hydrothermal constants. So these 9 mechanical properties means 4 elastic properties and the 5 strength properties. So we will discuss what are those 4 elastic constants and 5 strength parameters. And the 4 hydrothermal constants are 2 for the thermal expansion and 2 for the moisture expansion. So moisture, so there are 13 constants. So we are going to determine those constants. Micromechanical analysis of composite. It refers to the composite, actually composite material involves the development of analytical model for predicting the microscopic composite properties in terms of the constituent material properties and the information of the geometry and loading. So the constituent materials are the fiber and matrix in micro level, and their combination will give us the structure. So we are going to determine the properties in the macroscopic level. Analysis begins with the selection of representative volume element, which is a very small element of volume from which constitutes fiber and matrix together, and it is constituent. The representative volume element is then subject to uniform stress or displacement along the boundaries. So RB is subjected to some uniform load and displacement. The resulting boundary value problem is solved by either stress functions, finite element method, or finite difference methods. Computational approach used in composite analysis. So composite is one of the material under analysis. So the computational mechanics is subdivided into length scale and time scale. And the length scale is in terms of molecular mechanics, micromechanics, mesomechanics, and macromechanics. We can determine or we can analyze the length scale of computational mechanics in terms of molecular or atomic level, micro or microscopic level, meso or in the millimeter level, and the macro in terms of metric unit system, and then the structural or the whole system, which is measured in terms of tens to hundreds of meters. And another category is the nano mechanics, and then continuum mechanics, then the structure or system. The computational mechanics also subdivided into time scale. That time scale is the analysis are divided into dynamic analysis and the static analysis in terms of time scale. So when we say this static dynamic, sometimes it can be quasi-static based on the time of interaction. For example, if the time interaction is less, then we can call it as a static. And if the event is occur within a short period of time, like an impact or a collision or a kind of motion, then it is dynamics. And sometimes if it is within either not static or dynamic, then it lies in between them, then we call it as a quasi-static analysis. So this is the analysis scales in terms of actually length scale this is. So in terms of length scale, we call nano scale. That is in terms of 10 to the power of -9. Okay, so that is nano scale. We call it as nano scale. And then the nano scales are synthesized to some scale. Then it is in terms of micro scale, that is unidirectional representative volume elements, or which is actually in terms of matrix and fiber separately, then it is micro scale. Then the next is mesoscale, which is larger than the micro scale, which is in terms of millimeter. We can measure this unit in terms of millimeter. So most representative volume elements which made from fiber and matrix, they are analyzed in terms of millimeter dimension. And then the macro scale will come. Actually, there is a transition between nano to meso to macro, which is macro on the laminate level and macro on the structure level. So this is a structure level or macro scale. So more huge structures considered in the macro scale analysis. So this is the classification. More clearly, the classification is having two loops. The forward loops from micro to macro level, that is known as a stiffness loop or homogenization loop. That means the materials are in the first phase, materials are in terms of fiber and matrix. These materials analyzed further for larger scale. Then meso scale will come, that is lamina scale or RVE scale. RVE means representative volume element. And then macro scale is a laminate scale, because laminas are stuck together to form laminate. And then the laminate will be further analyzed to the structure level, that is called macro scale. So the loop in the forward direction is stiffness loop, or what we call it as homogenization loop. So the stiffness or homogenization loop is easily represented here, from a representative volume element to lamina, and from lamina to laminate. Okay, so this is the loop or stiffness loop. And another one is the backward loop, or here from macro level to micro level. So how it goes? And this the structure is impacted with a spherical ball, that is a laminated structure here. This is a laminated structure. I can call it as laminate. This laminate is impacted with ball. This is impactor. So when it is impacted, we have to know the characteristics of the local characteristics of the material on the deformable plate or the deformable laminate here. So there are a number of damages occur on the macro scale because of the impact by rigid impactor on the laminate. So that this behavior must be analyzed to the next step, to the meso level, taking individual plies and the damage on each of the ply. For example, if this is 0 direction and if this is 90 direction, taking the 0 dimension, taking the 19 dimension, we separately analyze it in terms of meso level on the fly level. From composite or from structure level to meso level, that is, and then further goes to the local damage or the local deformation of this thing, to know what is the damage in fiber, what is damage in the matrix, that is compressive damage in the fiber or compressive damage in the matrix, or tensile damage in fiber or matrix, those things, or if there is an internullar separation like delamination in the structure, that will be easily analyzed in the meso and the macro scale. So this is the stress loop or localization loop. So when we come to the micromechanics, that we start from fibers and from matrix. Then fiber and the matrix are combined together in a proportional manner based on the requirement. Then we can get lamina. And then these laminas are stuck together to form laminate. And from the laminate, finally we get the structure, which is the required part. So the mechanics in between this is called micromechanics. So what the representative volume element means, that it is a small part of a given structure. Just for example, if we take this part from this, we can get representative volume element, or we sometimes may call it as a representative unit element. And then this representative volume element is subjected to some loads in its actual performance. So this is the meaning of actually representative volume element, or a smallest unit which we can make analysis for the whole structure, that is a representative volume element. So this micromechanics is it is the analysis of a relationship between effective composite properties. It is in between effective composite properties like stiffness and strength are effective properties, and the material properties, relative volume contents, geometric arrangement of the constituent material. So this is actually non-homogeneous or a material made from fiber and matrix, and this is homogeneous lamina, means it is material of like aluminium sheet, for example. It is considered homogeneous lamina for isotropic homogeneous material. Mechanics of material models, actually we use different models. One is mechanics of material model, another is theory of elasticity model, and there is some empirical or explicit models are also there. So in the case of mechanics of material model, simplifying assumptions make it unnecessary to specify deals of stress and strain distribution. Fiber packing geometry is arbitrary, and in the case of theory of elastic model, that is actual stress or strain distributions are used. Fiber packing geometries are taken into account, and there is a closed form of solutions for this type, and numerical simulations solutions such as finite element modeling and variational methods are used. So now let's directly go to the properties The first one is the volume fraction. So consider a composite consisting of fiber and a matrix. That two constants are most of the time considered. So then the fiber volume fraction is given by volume of fiber over volume of the whole composite. BC implies volume of the composite and the BF is volume of the fiber. So volume fraction is a unitless quantity which is represented in terms of percentage. So maybe this may be 60%, or we can represent it in terms of percent. Okay, so volume of matrix is represented with volume of matrix, volume fraction of, this is the volume fraction, the volume fraction of fiber, volume fraction of matrix, volume fraction of void. So while in manufacturing process there is a small void is expected in the system or in the structure, so that the actual volume of the material is greater than the exact volume, because we simply calculate the volume of the actual composite in terms of its length, its width and its thickness. So when we calculate the actual volume, there is voids inside the material. That void is not considered, so that the actual volume is greater than the experimental, or it is theoretical volume is greater than experimental. So that must be considered in the analysis. So void volume fraction is volume of void in the given composite lamina over the total volume of composite. So finally we sum up all of them together to get one. Why? Because we represent this thing to some percentage. For example, if this is 60, this should be let it be 9.5 let it be percent. Then the void is about 0.5%. 0.5%. Okay, so the total sum of this thing gives us 100%. So that is equal to volume fraction of fiber plus volume fraction of matrix plus volume fraction of void, which gives us 1. So the composite volume totally is equals to volume of fiber plus volume of matrix plus volume of void. Now mass fraction, this is the another thing. So the mass fraction is also represented in terms of the fiber weight fraction, matrix weight fraction, composite weight. So what weight fraction of fiber is equals to weight of fiber over weight of the composite, the total weight of composite. And the weight fraction of matrix is weight of matrix over weight of composite. So finally we can calculate the total weight of composite, which is equals to the weight of fiber plus the weight of matrix. So this is also calculating how we can calculate the weight of composite. The weight of composite is equals to density of composite times volume of composite. So the total weight of the composite. So what is the weight of fiber? That is density of fiber over volume of fiber. And this is elementary definitions. We know this thing. So the total weight of composite is equals to the weight of fiber plus the weight of matrix. So which is we can rearrange and get weight of fiber in terms of density of fiber and the matrix in terms of, so this is the weight of fiber, this is weight of matrix. This is also the total density of composite is equals to density of fiber volume fraction of fiber plus density of matrix volume fraction of matrix. This rule is known as the rule of mixture. We call it as rule of mixture. And the density of each components or density of the composite can be calculated from weight of component. Composite is equal to the weight of fiber plus the weight of matrix, so that the weight of composite means this one. Okay, so and the weight of fiber is this one again, and the weight of matrix is this one. So from this relation we can rearrange it, and we can find the density in terms of the weight fraction of 1 over density of composite is equals to the weight fraction of fiber over density of fiber plus the weight fraction of matrix over density of matrix. So this is weight fraction. And the weight fraction of fiber is equal to weight of fiber over weight of composite, which is given us like this. And the weight fraction of matrix is equals to, that is density of matrix over density of composite. In terms of density, we are representing it. So how we can represent the representative area element for how we can idealize different types of packaging geometries in analysis. Sometimes we have a square array of fibers in the matrix, or sometimes we have hexagonal array of fiber arrangement, or sometimes it can be randomly distributed fibers. So that may happen. So here the fibers, these are fibers, and the hatch line or the cross section of hatch line indicate the matrix. So the square array of fibers. So the diameter of fiber is represented with D. The square of the matrix region is represented with S. So actually we have this this D and S as function. That's why we put it here. So we will see the ratio of D and S. And this is rectangular array. No, it is triangular array here. Fiber arrangement in triangular array. This is actually in the case of hexagonal type. So the volume fraction in terms of, in the case of square array, the volume fraction is given as pi over 4 D over S. So this is the ratio. D over S is ratio. Still, this volume fraction is unitless quantity. You can easily prove it from here because D is in meter, S is in meter also. So if S is equals to D, in actual case, the diameter of fiber should never be equal to the diameter of the length of the matrix, but let it be. So if it is so, the volume fraction becomes 0.785. That means the fiber volume is bigger, means like this actually. We can sketch it like this. This type of, so this is a D, diameter. This is a diameter of fiber, and this is, we can say this as D, and this is S. Sorry for the poor writing here. Anyways, so if S is equals to D, that means the volume fraction is, no, the ratio of, actually volume fraction of this type of array is 0.785. And then in the case of triangular array, the volume fraction is given in terms of pi over 2 rho radical 3 d over s. So in the case of s is equals to d, then Vf is equals to 0.907. So this implies the volume fraction is too much in this case. So whenever we need too much volume fraction of fiber, maybe hexagonal arrangement is prepared. But most of the time the volume fraction of fiber is in between of some 55 up to 80%. So it may not be 0.907, that means 90.7%. This is some material property for some typical fibers: graphite fiber, glass fiber, amide fiber. This is the fiber in the SI unit, material property for fiber. Okay, these are some three fibers. We can use these values further in some calculations. That's why I placed it. Okay. These are the metric property. The metric property: axial modulus, transverse modulus, axial Poisson ratio, transverse Poisson ratio, axial shear modulus, coefficient of thermal expansion, coefficient of moisture expansion, axial tensile strength, axial compressive strength, transverse tensile, transverse compressive, shear strength, and specific gravity. So these parameters are useful in further calculations. So in both cases you can see them. Okay. So most of these things are given in terms of SI unit. For example, we can take one example here. Glass epoxy material, that is, glass is a fiber, epoxy is a matrix. So glass epoxy material having 70% of fiber volume fraction. So BF is given 0.7. Use properties of glass epoxy from table 3.1 and 3.2. Look, these are glass is this one. In 3.1, glass properties are these properties. Okay, this is glass property. This is. So we can use these properties. Okay, so glass epoxy. So where is epoxy? Epoxy is the matrix material. So this is epoxy. So we have given here three matrix material. Epoxy is one of the matrix material, and polyamide is another matrix material. So now epoxy material properties are these properties. Okay, so using this property, we are going to find density of lamina. We are going to find mass fraction of the glass epoxy, and we are going to find volume of composite lamina. That means the volume of the lamina itself. If the mass of the lamina is 4 kg, its mass is given 4 kg, and the volume and the mass of glass and epoxy in part C means volume and the mass of the glass, volume and the mass of the epoxy, just taking C as an input. So the solution will be that density. So from the table 3.1, density of fiber and density of matrix. Actually, this density of matrix is from table 3.2. So density of fiber is this, and density of matrix is this. We can see once back. Let's go. What is density of glass? The density of glass is, we can take from this specific gravity. This 2.5 means that represents the density. Okay, 2.5. Yeah, 2.5 is that means multiplied by 1000 by multiplying the density of water. Okay, specific density or specific gravity means it is the density of an object is divided by the density of water. So that's why it is called the specific density. So that specific density 2.5 means the density of that object is the specific density of glass multiplied by the density of water, that is 1000. So what is the epoxy? The density of epoxy 1.2 means 1200 kilogram per meter cube. Okay, so 1200 kilogram per meter cube. So the total density of the composite is equals to density of fiber, volume fraction of fiber, plus density of matrix, volume fraction of matrix. Then finally we get this. The second is mass fraction of the glass and the epoxy. What is the mass fraction of glass? What is the mass fraction of the epoxy? So the weight of fiber is given in this formula as we have derived earlier. So the weight fraction is of fiber is 0.8294, and the weight fraction of matrix is given in this formula. So the weight fraction of matrix is this. The sum of this weight fraction of matrix and then weight fraction of fiber gives us 1. So which is the sum of the two is 1. The next, the volume of composite when mass is given. Okay, we already calculated the density of composite. So the volume of composite is equals to weight of composite over density. So that weight is equal to density times volume, as we know. So which is 1.896 times 10 to the power minus 3 meter cube. That is the weight. Once we get weight, the volume of glass and epoxy, the mass of glass and epoxy, we can calculate them. The volume of fiber, that this glass is fiber and the epoxy is the matrix, so that volume of fiber is given in this formula. So volume fraction of fiber times volume of the composite. Okay, so 0.7 times the volume of composite, then we can get this is the volume of fiber. The volume of matrix is volume fraction of matrix times volume of composite. Volume fraction of composite actually. Yeah, volume fraction of matrix times volume of composite. So what we can get, this is the volume of matrix. So weight fraction of fiber is the density of fiber times the weight of fiber, which gives us this value, and the weight of matrix is equals to density of matrix times volume of matrix. So we can get this. Another thing is the void. So void is the coherent defect. It is a defect in a composite. We consider there are a number of defects. So void is the one. Different types of voids happen because of some manufacturing imperfections, because of some deficiency in the manufacturing process in general. So that void has an effect in the total strength of the material. Anyways, so during manufacturing, composites consist some void, and this causes the theoretical density of the composite to be higher than actual density. So the void volume fraction is given as the volume of void divided by the volume of composite. So the total composite volume is the sum of volume of fiber plus volume of matrix plus volume of the void. So the volume of composite is the weight of composite over density of this. E implies experimental, and here T implies theoretical. Okay, so E and the T, the subscripts E and the T indicate that density of composite, theoretical composite, density of experimental and theoretical. So weight of composite over density of composite experimental, which is equals to weight of composite over density of theoretical composite plus void volume. Okay, so void volume fraction. Then we can get the void volume as void volume fraction, which is equal to void volume divided by the volume of the composite. So the void volume is equals to this parameter is equals to density of theoretical density minus experimental density or actual divided by the density of theoretical. So that from this we can get the void volume fraction. So we can find, we can do some example on that. So graphite epoxy, still we are talking about graphite epoxy of specimen having cubic dimension. That means the dimension of the specimen is ABC, which is equals to equal. That means maybe the cube dimension of material, and we can take maybe A this is B and this is C. Sorry, A. Okay, so yeah, it's C already. So volume fraction actually has dimension of, and its mass M. Mass is given as MC. After putting it in the mixture of sulfuric acid and hydrogen peroxide, the remaining graphite fibers have a mass of F. From independent tests, the density of graphite and the epoxy are given as rho of F and rho of M respectively. So find the volume fractions of voids in terms of A, B, C. A, B, C are the dimensions. So volume fraction of the voids in the in terms of ABCD is given as BC is equals to BF plus BM plus BD. So volume fraction of fiber is volume of fiber is mass of fiber over density of fiber, and volume of matrix is mass of composite minus mass of fiber over density of matrix, and the total volume VC is calculated as A times B times C. So this implies A times A times B times C. So that is the volume of the total composite, this two ampulla A, B, C. Okay. So ABC, the total volume is equals to that is volume of fiber plus volume of matrix plus volume of void. So which is equals to volume of void is equals to volume of void over the volume of composite from the definition. So which is equals to 1 minus this formula. So alternatively we can also use this formula. Okay, That means 1 minus BF means it is Bm. That is volume fraction of matrix. This represents volume fraction of matrix, because volume fraction of fiber plus volume fraction of matrix is equals to 1, which implies volume fraction of matrix is equals to 1 minus volume fraction of fiber. So this implies volume fraction of matrix. So from that we can get the experimental volume density of the composite, which is equal to mass of composite over volume of the composite, and the fiber is given in this formula. So the next topic which we are going to see is how we can find the 4 elastic modulus. Actually, the basic aim of this chapter is to determine 4 elastic constants, 5 strains parameters, and 4 hydrothermal properties, that to the moisture terms and to the thermal expansion terms. So among them, the 4 are actually certain parameters which we are going to determine. So from them, let's see the 4 elastic properties in the unidirectional lamina, UD. This is UD lamina. So the one is the longitudinal strain, another is the transverse strain, and the major Poisson ratio. Once we get major Poisson ratio and the in-plane shear modulus, then we can find the others by using Maxwell reciprocal theorem. So the 3 approaches we use to determine these parameters or elastic modulus are strains of material approach, semi-empirical approach, and elasticity approach. So let's see the strains of material approach first. So in the strains of material approach, we can take lamina. This is a lamina. Okay, so this is lamina. So from this lamina we can take a small volume, a small representative volume, and this implies that the small representative volume, that is called representative volume element, RVE. So this is our RVE. We already discussed what RVE in our today's lecture, so that this is RVE. So we'll take this RVE for further analysis. So the RVE of the unidirectional lamina. So we can see this cross section or hatched line as the matrix, which is not matrix, it is a fiber there, that is considered a fiber. So the area of fiber is equals to thickness of fiber. You see, this is we call this area as area of fiber. So what is the area of, actually by considering the full this thickness of this thing, RVE, we consider this thickness. So thickness of fiber, the remaining are thickness of matrix, okay, and area of fiber is equal to thickness of fiber times h. H is this thickness. Again, area of matrix is equals to thickness of matrix times this height also, and total area is equals to area thickness of composite. This is thickness of composite from here to here, thickness of composite times height. So taking the overall these areas, considering all this area, so area of composite. So the volume fraction of fiber is equals to area of fiber over area of composite. That is uniqueness quantity, as you see. Volume fraction of matrix is equal to area of matrix over area of composite. So which is equals to this Vm is equal to 1 minus Vf. So this Vf is equal to thickness of fiber over thickness of composite, because we can use this formula. Finally what we can get is this one and this one. So there are certain assumptions are required here. The basic assumptions in the analysis of this, in the determination of the elastic constants, the bond between fiber and the matrix is considered perfect. That means there is no interfacial debonding in between fiber and the matrix. At the point where fiber and the matrix are connected or bonded, the interface should be perfect. The elastic moduli, the diameter and the spacing between fibers are uniform, and the fibers are considered continuous and parallel. So there is no waves in the length of fiber. We consider only straight fibers. Actually, in actual case, there is a wave or there is a kind of curvature in fiber, but we consider the continuous and parallel fiber only here. And the fiber and the matrix follow Hooke's law. That is, it follows the law of elasticity or linear elasticity. And the fiber possesses uniform strengths. That means the strengths in every length, the fiber strength should be the same. And the composite is considered free from void. That means we are considering a perfect manufacturing of composite. So let's see how we can determine the longitudinal longest modulus, that E1. So this is our RVE. As we have taken it from the total lamina, we cut from the lamina and then we got a small RVE. So this is our RVE that we took it from the previous picture. So this RVE is subjected to axial load. Okay, so while we are subjecting it to axial load, there is matrix here. This is the fiber, the middle section is fiber. Actually we can also add matrix here, no problem. So it is subjected to this load. The fiber and the matrix are together subjected to axial load. Then the force applied is the sum, the total force is on the composite is sum of force on the fiber and force on the matrix. So what is the force on fiber? That is stress on the fiber. Actually this is directly from the equation of equilibrium. There is no such huge different logic on it. So that force on the composite is equal to stress on the composite over area of composite. As we know, stress is equals to force over area. Okay, as we know from strength of material or from statics or any kind of mechanical subject, as we know, if we have some cross-sectional area A here and applied force F, then stress is equals to force over area. Okay, force over area. So that force is equals to stress times area is distinct. So force on the composite is equal to stress on the composite times area. Force on the fiber is equals to force stress of in the fiber times area of fiber. Then we can finally get this thing. So This is the formula which we obtain from this relation. So what is stress in the fiber? Actually here we can represent the stress in terms of the elastic constant, the Young's modulus, no, actually the longitudinal modulus or modulus in one direction times the composite strain in the composite. Again, stress in the fiber is equal to the modulus, Young's modulus in the fiber times strain in the fiber. So this strain means it is change in lengths over the original length, as we know. Strain is equals to which is equals to change in lengths over original lengths. That's a simple definition from the strength of material or static or other courses. So the longitudinal modulus, finally we get this formula, that is E1, which is Young's modulus in the one direction, that means in the fiber direction, the load applied in the fiber direction, so that we can get EF volume fraction of fiber plus Young's modulus of matrix, volume fraction of matrix, or sometimes we can, not sometimes, most of the time we can represent it as EF VF plus EM times 1 minus VF to minimize the VM quantity. So we can represent it like this. So this diagram represents the Young's modulus with volume fraction for particular materials, for glass epoxy, for tungsten, aluminum, copper. So this is some picture of relating the volume fraction with so maximum number of volume fraction is 1, that is the sum of fiber volume fraction from the sum of matrix volume fraction. Okay, so this is also another approach how we can find the ratio of forces. So let's go to some example. So find the longitudinal elastic modulus or of unidirectional glass epoxy lamina with 70% of volume fraction. Use the appropriate glass epoxy data from tables. Already tables are provided, and find the ratio of load taken by the fiber to the composite. So this is the load taken by fiber to the composite, this ratio. The question here implies loads taken by fibers to composite means this load. Sorry. Yeah, this load. So given we can take this thing from directly from table 3.1 and 3.2, which I provided at the very beginning. So the fiber volume fraction is 85 gigapascal, and the matrix is the epoxy matrix 3.0 gigapascal. This is for glass material. So we can actually go back to refer the table. Yeah, epoxy. This is fiber. So the fiber 85 axial modulus means the longitudinal modulus, that is 85. Transverse modulus also 85, because we consider fiber as uniform. And when we come to epoxy, axial modulus of epoxy is 3.4, transverse modulus. You see, that's why we call this material are separately when we consider them they are isotropic materials. There is no directional change of behavior. But when they come together, when they formulate another material, that is the so-called composite, then the anisotropy will come after. Okay, so we can, 8.5 and 3.4. Then using this formula, EF fiber force in the fiber over force in the composite, that is the load taken by the fibers to that of composite is 8.5 over 60.5. That 60.5 is E1. E1 is calculated using the volume fraction of fiber, because once the fiber volume fraction given 70% means the volume fraction of matrix is obviously known, that is 0.3. That means 1 minus volume fraction of this value is equals to 1 minus volume fraction of fiber. So if volume fraction of fiber is 70% or 0.7, then this is 0.3 obviously. Okay, 0.3. So that is 60.52 is a E1. One thing we must know here is what is E1, what is EF. E1 is the homogenized material property which comes from fiber and matrix combination. But EF is the Young's modulus of material in the fiber direction only, or it is only of the fiber. And the Young's modulus of material in the matrix is this. So in between them, this material property is obtained from the two, EF and EN. So it is a combination of the two properties. Okay, so that is different from the parental material. The value also here is completely different from, it is neither 8.5, it is nor 3.4, it is 60.52. That is a combined property. That means what we are doing is we are homogenizing the material. Anyways, so the ratio is 0.9831. The next is transverse modulus. That is the modulus of material or the elasticity of material when load is applied in the transverse direction. That is the direction perpendicular to the fiber. Fiber is in this direction and load is applied in transverse to the fiber direction. So this is the fiber direction is toward this to here, but load is applied like this. So this is fiber matrix, so load is applied like that. Okay, that is different from the previous. So during this time, the stress in the composite is equal to the stress in the fiber, and it is equal to the stress in the matrix. That means the deformation of composite is the sum of deformation of fiber plus the sum of deformation of matrix. You see, when this load applied in this direction, deformation of this fiber plus deformation of this matrix. Deformation is the sum of the two this time. In the previous case, the deformation is the same because we are applying in the direction of fiber. So both fiber and the matrix deform equal. But this time deformation is the sum of the fiber deformation and the matrix deformation. So this is so from this deformation of composite is the thickness of composite times the strain in the composite. And the strain in the composite is equals to stress in the composite over E2. This is in the matrix direction actually. So E2 is the one which we are searching for. Okay. So deformation of fiber is equals to thickness of fiber times the strain in the fiber. Deformation of matrix, thickness of matrix times strain in the matrix. So finally, what we can get is okay. So this is 1 over E2 is equals to the volume fraction of fiber over the strain elastic modulus of fiber plus volume fraction of matrix over elastic modulus of matrix. So this is a reciprocal relation in this case. And the axial direction, it is directly the sum of the elastic modulus of fiber, volume fraction of fiber plus elastic modulus of matrix, volume fraction of matrix. But in this case, it is reciprocal. So let's take a small example on that. Still the same material we are using because this material is appropriate for our analysis, and to avoid some other confusions, let's use the same material. So 70% volume fraction. What we are going to find the transverse modulus. This is the required material, the parameter. So 1 over E2 is equal to volume fraction. This already the given formula. From that we can calculate the volume fraction of fiber 0.7, the volume fraction of matrix, the Young's modulus Young modulus 8.5 for fiber and 3.4 for matrix. So this is the elastic property of the combined property. So it is still greater than 3.4, less than 85. It is another material now. It is not that epoxy, or it is not now a glass. So it is glass epoxy composite in the transverse direction. Now the fiber packaging geometry or array, how we can package. Sometimes we use a square array of fiber or a square packaging of geometry, or sometimes hexagonal package. So this formula we already seen it at the very beginning, but it is useful so that D is the diameter of fiber, S is the size of the given square array or the matrix dimension, so that D over S is related with the volume fraction of a given geometrical array of material, so that it is helpful parameter. And for this case we use this formula. So this is volume fraction of fiber over pi. Okay, 4 times volume fraction of fiber over pi. 2 radical 3 volume fraction of fiber over pi. That's the whole 1 over 2. Or we can make it radical of this thing. So we can put it as radical of 4 VF over pi. Okay. The next parameter is major Poisson ratio. But actually in mechanical loading, when we are applying load in the longitudinal direction, there is an elongation in the longitudinal direction, which is directly related to the compression or distortion or contraction in the size in the lateral direction. So this happened because of the presence of the Poisson effect. So that Poisson effect is represented with the help of Poisson ratio. So as we know that strain in the longitudinal direction is equal to change in length in the longitudinal direction over the original length, that is strain in the longitudinal direction. And at the same time, the strain in the lateral direction is represented as a negative change because it is reduction, because original dimension is greater than the final dimension, so that change in L is negative, so that the lateral dimension will be the strain in the lateral direction is change in lateral dimension over the original dimension of the specimen. So that the negative change in the strain in the lateral dimension over strain in the longitudinal direction is known as the Poisson ratio. So that is what? So a major Poisson ratio is defined as the negative or ratio of normal strain in the transverse direction to the normal strain in the longitudinal direction when normal load is applied in the longitudinal direction. So that is, so you see here, sigma 1 is applied here in the longitudinal direction. So when this force applied, we can find change in length here, a positive change in dimension. So here what we can get is final dimension is greater than the initial dimension, so the change in length is positive. Then the strain is equals to change in length over the original length. And in this lateral direction, the deformation from original to the next is here negative change. So that will give a Poisson effect. So now the deformation of composite in the transverse direction is equal to deformation of fiber in the transverse direction plus deformation, because deformation is the sum of the two. They are all in the same direction. So strain in fiber direction is equals to deformation in the fiber direction over deformation in the thickness of the fiber, and the strain in the matrix is deformation of matrix over thickness of matrix. So from this relation, taking this one and substituting these parameters to here, we can get this is transverse strain of the composite. So for that we substitute it in terms of this parameter. Finally, volume, the Poisson ratio of fiber is equals to strain in the fiber over transverse direction over strain in the longitudinal direction. Poisson ratio of matrix is equals to minus of transverse matrix strain over longitudinal matrix strain, and then the substituting these values to this formula, finally we can get this relation. This relation, either this one or this one. So basically this is the formula of the Poisson ratio. That is the Poisson ratio of fiber times volume fraction of fiber plus the Poisson ratio of matrix times the volume fraction of matrix. Okay, this is not reciprocal, but it is the direct. So find the major Poisson ratio of glass epoxy material. As we know, that material is already known. So BF is already given there, BM is given, E1 is already calculated. We calculated it in the previous section. E2 is already, we calculated it. So we can substitute the value of this thing here. Okay, so then what we can get is 0.23, and this is the minor Poisson ratio. How we can relate it? We have this type of relation, mu of ij, over E of I is equals to that I mean mu is the Poisson ratio of Ji over E of J. This is called the Maxwell reciprocal theorem of the thing. So the Poisson ratio, the major Poisson ratio of in the Ij over the youngest modulus in the I direction, which is equals to the Poisson ratio of Ji over the youngest modulus in the J, which is which helps us to relate this value. So from that we can get this answer. The next is in-plane shear modulus. So this in-plane shear modulus is found by applying a shear load. Okay, shear load in the that is T tau. That means, for example, tau 1, 2, and which forms a deformation of the structure like this. Okay, so that the shear deformation of the composite will be obtained from the deformation of fiber plus deformation of matrix, because both of them deform. So deformation of matrix is related is the shear strain. The shear strain of the composite times thickness of the composite. This is the shear strain. Here the strain 1, 2 implies the shear strain. So in the fiber, shear strain times thickness of fiber, in matrix, shear strain of matrix times thickness of matrix. So finally what we can get is this is the relation. So this is shear stress, tau c means the shear stress in the composite times thickness of composite over the shear modulus of the composite, 1, 2 direction, that means major direction, which is equals to the shear stress of fiber times thickness of fiber over the shear modulus of fiber plus shear stress of matrix times thickness of matrix over the in-plane shear modulus of matrix. So this relation finally gives us this formula, which is reciprocal 1 over G 1 over 2. Then G 1 over 2 means the in-plane shear modulus, which is equal to volume fraction of fiber over shear modulus of fiber plus volume fraction of matrix over shear modulus of matrix. Sorry. So we can find it, we can calculate it here. How we can calculate, these formulas are directly come from the material property of isotropic. We consider fiber as isotropic, matrix as isotropic material, so that for isotropic homogeneous material we have this relation. The shear is modulus is related to its youngest modulus and with Poisson ratio in this form, in this manner. So it is directly come from there. So we will find GF, which is equals to this. We calculate GM, or the shear modulus of matrix, this, and finally we have to find the shear modulus in the 1, 2 direction. This 1, 2 in our case, 1, 2 are the local material axis directions, the direction in the material axis. So when we say 1, 1, when we say 1, 2, when we say 2, 2, they are the material axis, or the direction, local axis of materials. So 1 over G12 is equals to volume fraction of fiber over GF plus Vm over Gm. So 0.7, 0.3 are the volume fraction of fiber and the matrix. So we directly substitute it and we get this. So the next is semi-empirical model. Okay. So Alphan and Tsai developed their model as simplification by curve fitting to result that are based on elasticity. So the equations are semi-empirical in nature because involving parameters in the curve fitting carry physical meaning. So these are formulas for longitudinal and transverse Young's modulus. Okay. So we have some additional parameter here. So the alpha and T equation for the longitudinal Young's modulus is given in this manner. This is for longitudinal and this is for transverse. So in this we have some other parameters. This parameter is given with this formula. And this zeta is the reinforcing factor, and depending on different parameters like fiber geometry, packing geometry, loading condition. So we can take some parameters relating this two parameters. So we can calculate if this is given to fiber Young's modulus noun, matrix noun for glass epoxy, and this formula is already given from the alpha and T formula. So we can get the neta value. Once we get this neta value, we can find the E2 value from here. This is directly, we took it from this formula. Okay, then E2 is this, and the major Poisson ratio given this relation, and in plane shear also given us like this. So we can also calculate these parameters. They measure the in-plane shear modulus in terms of alpha and T formulation. Okay, so the last or the third part is elasticity approach. So in elasticity, which accounts for equilibrium force compatibilities and the Hooke's law relations in 3 dimensions. So here what we are looking is the property of material. For example, if fiber, for example, this diagram shows the fiber behavior, that stress-strain diagram of fiber. So fiber having higher ultimate strength when compared to this matrix. This is matrix. Matrix having lower ultimate strength, but the toughness of matrix is higher, but the toughness of fiber is very less. So most of the time our design is depend on the fiber material. We cannot go beyond the fiber region. So that, for example, if we take composite at this level, so the failure strain, the ultimate failure strain of the fiber is here, and the ultimate stress of matrix is here. So the combination of the two should be somewhere around here. So this is the matrix, not matrix but the composite. This is for fiber, and this implies for matrix, and our composite is in this region. Maybe someone design it to this point, someone may design it to this point or this point. It depends. So this is the combination. So what is the ultimate strain of fiber? That is defined as the ultimate stress of fiber over the elastic modulus of fiber, and of matrix, ultimate strain of matrix, that is ultimate strain of matrix is this one, which is equal to sigma of matrix, ultimate stress of matrix over. So this implies the slope of this thing. Please, it is simply the slope of this thing. Okay, this EM is the slope of this thing, and EF is the slope of this curve. Okay, EC, the composite slope is this E of composite. Okay. So longitudinal tensile strains, actually we are here finding strains, not the elastic constants, but we are finding the strains. Okay, ultimate strains of in the transverse direction. So the ultimate strains of transverse direction is calculated as the stress in the fiber, the ultimate stress in the fiber times volume fraction of fiber plus strain in the fiber, ultimate strain in the fiber times, actually this implies sigma of, this is sigma of matrix. No, this is 1 over this, yeah, this is sigma of matrix times volume fraction of matrix. Okay, so these are relations. Actually, there are two values of fiber volume fraction. The minimum fiber volume fraction required. The minimum fiber volume fraction required is given with this formula. That means sigma of ultimate matrix times En, strain in the fiber of ultimate strain over sigma ultimate of fiber minus youngest modulus of matrix, strain of ultimate strain of fiber plus stress of matrix. So and the critical fiber volume fraction, that in the design there must be some limitations. So the limit, the critical one is related with this formula. So this is the critical volume fraction, and this is minimum volume fraction that we can limit. So this example also illustrates how this strains parameters in terms of stress and strain, okay, based on the Alphonse, based on the SART approach. So parameters are already given. Required is the fiber ultimate strain of fiber, ultimate strain of matrix, and what is the strains of the ultimate strains of in one direction. Okay, so this is the ultimate strains of one direction based on this formula. And what is the minimum volume fraction required? So this is the minimum volume fraction from the above formula. And what is a critical volume fraction? This is the critical volume fraction that required. So now another important thing is how we can experimentally check the longitudinal tensile strength. So in experimental work we have to prepare the specimen, proper specimen. So this is a standard specimen which is used in the geometry, and the longitudinal tensile strength specimen is placed. So the thickness of specimen is given here. The gauge length, that is about 153 millimeter given. Total length 229 millimeter, and there are tabs here, okay, that expect up to 3.2 millimeter, and the tab length is given, and the angle. So this is the arrangement of specimen for tensile test. So this is the tensile testing machine. Actually, there are ASTM standard tensile testing setups at this time, and different types of setups are there. Actually, some of the Boeing company setup, some of the composite material setup, some of them are ASTM, ISO, and so on. A lot of setups are there. So this is an example of one of the setup for longitudinal tensile strength check. And this is the stress and strain diagram for the longitudinal testing. So and what are the failure modes occur when we are subjecting a given specimen to tensile test? There are some type of failures are occur on the material. One is the complete rupturing of the material. Another is a fiber pull out, kind of fiber pull out, as we see here. From this fiber is pulled out from here, and at the same time breakage of matrix, breakage of fiber. Here also some shearing occur, shearing and rupturing of materials. So these are failure modes in the case of tensile loading, tensile strength test. So longitudinal compressive stress. Now let's see the compressive stress. When the specimen is subjected to compression, what are the strength parameters? So we are express them in terms of the absolute value. So the strain is absolute value of strain is related with the absolute value of stress with E1 for strain in E1. Strain in E2 is related with E sigma 1 and E1 using the Poisson ratio. Okay, so that is when the loads are applied in the direction of 1, 1, so that the second direction is having a Poisson effect, so that we consider that. So these are the strains of compressive strains of 1 is given with this formula. Okay, the compressive strains of 1 is minimum of S1 and S2. So what is S1? S1 is given like this. Okay, in terms of volume fraction, okay, in terms of matrix, youngest modulus of matrix, youngest modulus of fiber, volume fraction of fiber. So these parameters, and the S2 here is, that is in relation to the in-plane shear modulus with the volume fraction of fiber. Okay. Another, these are also the relations that the ultimate strains of shear strains of 1-2 direction. This is shear strains or shear stress in the 1-2 direction is given as the shear strength of fiber, volume fraction of fiber plus shear strains of matrix and volume fraction of matrix. And ultimate tensile strains in one direction, that not tensile but compressive strains, compressed in one direction. What I am saying, the specimen is compressed in fiber direction. The loading is compressive loading now. See. Okay, so our fiber is here. If you consider this as fiber, so what are the failure modes in the compression? There are different failure modes in the compression. Basically, the fiber microbuckling is the one type of. So extension type of fiber microbuckling, this is extension type. Okay, so as you see, it is extending outward from here and here. This is called the extension type of fiber microbuckling. This is also compression or shear buckling. In this, it is considered a shear buckling. Another failure is transverse tensile failure of matrix. So there is a matrix failure around here. Okay. And also shear failure of complete shear of matrix. This is a type of failure also, especially when it is applied in the lateral direction. Okay, so there is also matrix micro cracking and the delamination at the interface also occur. So these are some of the failure modes in the longitudinal compressive loading. Okay, so this table gives some experimental values for longitudinal compressive strains of some particular material. So for glass, polyester, glass is fiber, polyester is epoxy, typical carbon epoxy, again Kevlar epoxy, three materials, epoxy materials. So these are the experimental strains. The strains from equation that currently from current analysis, and this also from other equations. Okay, so based on the above equations, we can calculate some parameters and using some values from the previous table. So what is the matrix strains? No, Poisson, no, what you call the strain in the matrix, the strain in the matrix in the two direction. Okay, so we found it from here based on some parameters, and the ultimate strains in the compressive direction, one compressive direction. So all parameters are there, so we can, it is a matter of substitution. Okay, so this is all about for today. Thank you for your patience. Thank you very much.